Hello, everyone. Okay, my name is Yu-Feng. I'm from OpenGeoHub. I really like to have a smaller room because it looks more compact, and also it can be more interactive. The big room, passing the question will be more difficult. So I really like this kind of setup. And today I'm happy to be here and talk a little bit about high performance computing in geomorphometry. And before the session starts, I would like to see. No, this is not wrong. Is it wrong?
Sorry, you left the call.
I left the call?
Yeah, maybe it's an internet issue.
Yeah. Okay, join now. Okay, and share it again.
Yes, please.
Allow. Entire screen. Okay, it's here. It's here?
Yes, perfect.
Okay. So first of all, I would like to you maybe access the GitHub so you can access all the material there, slides, and Jupyter Notebook, and kind of supplementary materials there. So if you go to Mattermost, Square, I already posted there. I have a section yesterday, so I also put it there. And today I will talk about the second section. It's about high performance computing geomorphometry. And if you go there, slides, click on it, you can find the same thing as I do for now. I see a lot of people join the slide, so very good. I think people can find it. So I'll do a brief introduction. Viola, can you please give me the time so I will not for scratch sometime. Do you have like
I can go get the time.
Yeah, if you tell me like 30 minutes, it will be okay. Yeah, thank you. So let's get started. I will do some introduction, I think around 30 minutes, more or less, and then do some coding, compile different software, and also I will showcase how can we do high performance computing in geomorphometry. So first of all, I will have to shout a little bit of this project. So it's supported by OpenGL, one of the OpenGL project co-operated miners. So we produce open development and produce open data for community. So in this project, we develop a lot of different source of solution for data hosting and computing larger number of data. So need to shout out a little bit. And coming to the section first, we will go through the elevation model. Do anyone ever heard about digital elevation model? Yeah? Yeah. So the elevation model is a model that kind of like record the surface height of the Earth. And then in the simplified version is the digital representation of the terrain elevation. So you will have each pixel which represent a height. And this height, for example, in Himalaya, it could be 8,000, and in the Netherlands can be -5. So that pixel grid will record the height of the surface So using that digital elevation model, we can derive a lot of things that we call in a geomorphometry concern. Why this is very important? Because most of the environmental study that related to elevation. For example, you have different climate in the different elevation zone. You have temperate climate. If you have a higher elevation, you have delta when you have like close to the coastline. So in this case, to map, for example, soil cover or different like a soil property, you will need elevation to see how water flow around the surface. So if you have more water in some places, you can really get wet, high soil moisture. And in the case that you have precipitation for sure, but this is one of the main also input when we do a lot of soil mapping. And also in OpenGeoHub, we also use a lot of this for machine learning training. For example, on the left side, you can see we map the soil type according to digital elevation model. And this is an example that different soil type has been reflected into into the like location according to the mountains. This is kind of like what I'm contributes to the project, and that's I record that for example the house shade, how many sun they get to each pixel, also impact how kind of soil will form at that places. And also we use that also to map the livestock density map. So also the for example, slope has been also correlated with the livestock movement, and also how the grass will grow and livestock will passing through. It also has an impact from the elevation model during this kind of biogeographic study. And we also do some global stuff for example, grassland classification, and also vegetation height modeling. That's also we use this terrain model to work with. And I really like one of the terrain feature in the open source development, open source community is the open topography. So this is one of the open topography. So this is a website that holds a lot of different digital elevation model here. So if you go here, the catalog, you can find there's a bunch of digital elevation model and high resolution terrain model. And this is a cloud-based surface. So you can go here and let me see, you can do data downloading by the API. So yes, I just play around. So you can define that what is the instant that you want to find. Okay, so I was tried it out. So whatever this is, whatever I wanted is to compare different digital elevation model, I will use this software to actually find out, to actually download this kind of area and then showing my QGIS. So I can define the special special instance for the layers and do it execute online and get this download. So request body download file. And for example, I just download. Yeah. And I can just open it. And I have a random digital elevation model on the download from the service, from download by this portal. And you can choose whatever different type of digital elevation model. Feel like your chat is compatible in my Telegram. So you can select SRTM or COPDEN or NASA DEM, and from JEDI, for example. So I really like this innovation, and also save a lot of us for developing because I already have a proper solution. So when we do data production, we also put on their surface. So shout out to Open Topography. Oh, okay. Let's go on. What is geomorphometry? So geomorphometry is a subject that actually started in 2009, as I remember, because we have a geomorphology and geoinformatic. And this is a guy who called Tom Sengel, and he's really enthusiastic about, okay, maybe we made this geomorphometry as like a subject. So we do geocomputing on morphology, digital elevation, using digital elevation model to create that, to derive different surface metrics, and they create all these subjects from 2009. It's from the guy who calls Tom Sengel and Hannes Rauter. And they wrote this book 2009 about geomorphometry and published in 2009. Now they have a second edition. So it will be coming soon, I hope. So this is the kind of like a start of the geomorphometry. So geomorphometry is, in a nutshell, it's a study of derived land surface metrics that from the digital elevation model that can represent different type of land surface movement and different like land surface features. So this is the start of the study. And this is, for the example, you can derive, for example, here, like a hair shade from a digital elevation model. You can see how these Andes is show up in the South America. And also different scale, like looking to is the Madagascar island. You can derive, well, for example, this is flow accumulation to see that how water flow on the surface to the sea. And also on the right side is the topographic index, and this is my island in Taiwan. So you can see that this, see this delta have a lot of flow accumulated, and in the mountain area, it's mainly like you can see this string like coming down to from the mountains to assumably some lower point, well, form as river if there are a lot of precipitation. So this is the brief introduction of geomorphometry. And on the state of the art of the research, we have a lot of people working on geomorphometry, but they found like the difficulty is actually upscale to a big scale, to higher resolution or more bigger area, that this become more of a problem of the computational issue, because some of the algorithm developing the 80s, they don't really think about scale up into global scale, but and also not think about scale up to high resolution. And when it comes to this kind of problem, we have this bottleneck. So there's one paper who trying to solve this issue to create this high resolution 90 meters geomorphometrical variables from MERT DEN is one of the first digital terrain model. And also the same guy, Giuseppe, he did done the same thing for hydrology 90. So it's the hydrological data set in the 90 meter resolution. And they have the licensing the CC BY, so people can just use this data for free if you do the research, which is very good. And then it's me. So I just published a paper this year about creating a more high resolution data set in 30 meters based on one of the digital elevation model that we create also in that paper. So so we create in that research, we create a digital terrain model from the from multiple digital surface model, and also combined with the LiDAR data, and we derive 15 different terrain variables to represent the terrain feature of the whole world. And this is why I would like to share a little bit of the experience I have throughout the time, and according to using this COAG example to show that how what is the struggle that I have met, and also how to really do that in the kind of semi-optimal. I would say I'm not the best, so at least have some breakthrough. Yes. And in this paper, the one of the thing I like is also we create this kind of multi-scale derivation. So we do two different resampling methods. We use the resampling method to resample the digital elevation model from the higher resolution to the lower resolution. So you can see that it represents into hydrological variables. You can see that this kind of white value is kind of the river stream. When you go coarser to coarser resolution, you kind of smooth out the surface. So you can see that some of the surface was black in the high resolution, but turned into gray or white in the lower resolution. So it can kind of have a sense of if you have more water at the time, this is the place is more sensible. And when they get filled out, because they have less elevation differences, when they get like, no, not less relevant, but get like a closer relation with this kind of wet pixels, they have been easier to approach, kind of like, how do you say this word? So more closer to the water. So this is one of the example for the multi-scale wetness index. So it represents that how wet the pixel would be on the topographic map. So also when the final resolution to the coarser resolution, you can see that some area are like a hotspot of consistently wetter pixel from the higher resolution to a lower resolution. This show up that those pixels has been more kind of like related to wet. So when we kind of overlay with this different resolution of the layers, it's also help for our machine learning prediction to capture up the information not only by the single image. So yeah, and also we have a main issue in the geomorphometry is most of the geomorphometry variables are neighbor related, because you have to know like how high your neighboring pixel is in order to know that if the pixel will flow to me or not. And the pixel, it's not usually related to only the pixel at your neighbor side, but also far away. So you can get the water from very far away, then it's just transporting to a specific point according to the algorithm. So in this point, we have defined terms we call like regional parameters or regional land surface parameters that differ from the local parameters because it's come from a not fixed area around each cell. So you don't know how far I need to search to get the water that will flow into my pixel. So this is the features that in the geomorphometry go. They are kind of like special dependent. And okay, so I'm going to show a little bit. This is the, if you see the global digital elevation map, and I don't know is that they make sense or not, but they are, the land are connected. So if the people in Spain, I just hey, Thailand, do the water from there also flow to me? Because our land is connected, so the water could also flow to my pixel. So that makes sense. So when you try to do this kind of big scale, it's not possible. You know, you're feeding all of the data from Spain to Thailand to Russia and Shikoka. I don't know how to pronounce the name right, but you have to reading in order to consider this kind of non-fixed pixel at the surrounding area. Maybe it's related to me, maybe or not. So it is hard to define when you try to do like a global scale. So what the current research they have done is to actually define a water shell. So the water shell is a unit, correct me if I'm wrong, water shell is a unit that the water will flow from the edge of the water shell, go inward into a specific area, and the water will kind of like form into a stream inside water shell and go into the ocean, or going to the next water shell, for example. So I think you can think about like duna basin or Rhine basin, that the river around the side will also flow into that river. So the water from different kind of creek or stream will all fall into the main river and go out to the sea. So you can define it as the water shell. So using that approach, we can actually know that the water will flow in between, inside this kind of water shell. They will not go above. So the Spain people don't have to worry about the water shell in Thailand, because the Thai water will not flow into Spain according to these definitions. And so realistically, there will be not also, because the water will not flow onto mountains and then cross down. So this is the way to actually distinguish the data so that we can do this kind of hydrology analysis. And then there's a problem that we also found is because when you define the water shell like this, is actually quite like data dependence, because if different data sets have different boundary of the water shell, and somehow like the small hill, they will be not seen as the water shell, so the water will still flow through the hill or not. So it's quite difficult to actually do the multi-scale approach. And then we found out if I can just do tile base for this, for doing this kind of analysis, and later on in this case we can fit into the memory, and we can parallelize the computing, because each tile have the same number of pixels more or less, and when you do computation you can actually also align different tiles. So in this water shell you probably will spend more time calculating the water shell which is around the Sahara, but you know, in Europe and Asia they have small water shell, they will be finished faster, and they will be like more difficult to actually to align computation speed around different water shells. So we try to see that if it function does work to actually make it to the tile. And then we tried one of the methods that we call it like overlapping. I didn't call it the name, but it's just overlapping. So we extend the tile first of all. So we have each tile which have like a boundary and border. But in this way, we to do this regional parameters, we increase the tile into a bigger tile. And then we do 2 tiles computation. So they have this kind of overlapping. So this is original. These are the small one are the tiles, the original tiles. And the big one is when this go to the computational tile, and they have some overlapping. And using this overlapping to see that if they can connect this kind of small water shell, so the water will not flow irregularly, not flow irregularly, and create this consistent at the borderline. And so in the conclusion, this method seems to be working. So that's why the paper get published. So in this tile, we have like 16% of the padding. They end up into some increase of the computation, but actually that solved the issue of this one, the kind of irregular tile will cause for the geocomputing. Yeah. And also, if you're interested in having this section, we also discussed to have using DGGS to actually compute this geomorphometry in the future, because we can have discrete grid cells that more efficient to store this kind of image in the way that. So if you're also interested in that, more like computation nerd, tomorrow there will be some DGGS section hosted by also my colleague David Consoli. You can also go there to listen. Yeah, and in this case, we kind of finalized a little bit of our approach. So this approach using this tile boundary, and then we can simply remove the artifact that, for example, this case is the Duna region, that we don't really see that much artifact around the tile boundary that you can see over here. So more or less is here. And this is the part of digital elevation model and geomorphometry. Does anyone have any question? Otherwise, we will go slowly to high performance computing, another different. Okay.
You were like doing this kind of thing,
Yeah.
on like a national scale data set, not the world.
Yeah.
And you knew like the catchment boundaries very well.
Yeah.
Would that be the best way would that be an easier way to do it?
Yeah, that's the most reliable way to do, I would say so. So it's pretty simple, because if you really have a do by but also it depends on how the country can derive their water shelf, right? So some country also relied to some mathematical conclusion to derive their water shelf, and sometimes you do by your own, it's more consistent. And so, but for national analysis, if you already have the official water shelf, to use that to derive the hydrology it's the best. Yeah, I would say. Yeah. Hello?
Okay, so I recognize most of these tools, but my question is for this job or this study, did you use all of these? Or what would be the main?
This one. So let me see. Yes, all of this, most of them. Yeah. Yeah, I'm sorry. We don't use the GPU chips, by the way. So I think it's one of the very downgrade. I'm sorry. This GPU chip I was still building up. I would consider like buy more in the future. Now we have one server only. Yeah, but it's not related to geomorphometry, right? Okay.
I have another question.
Yes.
So you showed that there was not like artifacts after finishing the tiles.
Yeah.
My question: how you kind of validate or verify that there was no, because if it's global scale, probably you're not checking one by one visual.
Yeah. So I don't know if I can do so. Okay. Let me see. I can actually check one by one visually.
No, yeah.
That is actually what we do. This one is not in the recording
Now you're sharing the presentation.
only. That's so sad. I don't know if I can share. I lost the connection.
I can still see.
It's very weird. Yeah, that thing we cannot. In theory, we do tile by tile, but eventually we're making the single layers and we check one by one to see if they really have like artifact in the boundary. In the first few rounds, we have serious artifacts, especially in the Sahara area. And I think that because we do field depression algorithm in the wrong way, we didn't have enough search distance. So the tile boundary effect didn't really help for that. So we have a quite bit artifact. So, but we fixed the problem after the second round. So yeah, we do see problem, and I think the problem could possibly be there. But with the data are all open online, so either I check or everyone can also check. I also have the GitHub repository, like when people report the issue. Yeah, okay. I mean, this is the strike, huh? The KPN strike.
Maybe I didn't get it.
Yeah.
So which was the topographical digital elevation model you used? Because you mentioned in the open topography,
Yeah.
several options.
Yeah.
So which is your favorite or use modern one?
The favorite one is myself. Oh, I have a. Okay. So this is the paper we published. So this paper is about we want, in order to derive the share. Oh, sorry, I need to share. Oh. Yeah. Okay. Do I have a window? Yeah. So this paper is about we derive a digital elevation model and derive all the terrain variables. And this model is based on ISAT and JEDI dataset with MERT dataset, MERT DEM and Copernicus DEM and the Atlas 3D world. And we do ensemble machine learning model and to actually create, remove the buildings and the vegetation from the surface models. The surface model are the Copernicus and the Atlas. And then we create one of the 30-meter resolution digital terrain model from that. And one of the novelty also I wanted to mention is the, yeah, four. Oh, 4. Yeah, I have 1 hour. Great. So one of novelty I want to mention that is this one. So well, in order to train the global model, we do a global. In order to train the model that's suitable for different different landform diversity. So we do like a global modeling, and then we train a global model, but we add more sample from the more LiDAR points from each tile to actually localize the context into a local prediction. And we made that into a single consistent terrain model that has kind of like harmonizing, so enhancing the local features in the global terrain. And this kind of talk we also covered yesterday from the cloud native factor format. If you are interested in, there's also the talk from yesterday. They talk about the JEDI. It's more or less using into this project also. So that's the digital terrain model that I use for deriving this stuff. Okay. Yeah, hello.
I will start first saying that CC pronounced Chukotka Peninsula very nicely at the Russian speaking.
Wow.
Then I have a question about padding, and how did you choose exactly the size of padding you use? Have you tried different options?
Yeah, first we try different option.
But it's pretty unstandard, 16.7% or something.
Yeah, yeah, it's true. First we try to see if we can do 1 degree of the increasing of the time, and also consider most of the water shell level, the size of the water shell, how will be the size of the water shell of the world, and based on that, we choose kind of like conservative overlap for this. So that will be my answer. It's not really optimized. I'm sure for some reasons it should be theoretically different type of water, different type of like extensions of the boundary, but this is theoretic. But in practical, it's will be too much fine tuning at the production phase. So this is kind of like compromise solution, as you probably read more data, read more useless data, and compute more useless pixel to get this result. There should be an optimized way, and but in our theory, that these optimized ways have been proposed by this person, this researcher, has been not very suitable when you do different scale of the digital terrain model. So it only every time you go to different resolution of digital terrain model, have to derive different water shell in order to produce the to produce this result. So that will be my answer.
Next one, let's follow up on your answer on the filling the sinks. And then are you filling the sinks on the face when you have this extended rectangle that you work, and then you crop the outside and merge it out? Yes. Or
yeah. So first we have the extended tile, and then we get the extended the red one. We fill the sink, and then we use that to derive the hydrology, all the parameters. And after like derive all the thing, we crop to the small scale. So we only use the data in this, and the outside we don't use. Yeah. Yeah. No problem. Okay, that's very good. Very good to have this question. And now we will go to high performance computing. I think you saw this graph from yesterday, like panel section from my colleagues, Leandro Balenti. So I just showed that this is kind of like infrastructure that we're using OpenGeoHub as a high performance computing. It's really like in-house stuff. And what I wanted to talk a little bit about is how we do high performance computing. And this is the one of the article that shows like a very simple practical way that what is the bad practice of the parallel computing, what is the good practice. So to be noticed, now we're talking about the parallel computing is in the data parallelization. So we have all this tile. We'll have all this tile, and each tile we go to do all the processing. So we call this kind of a scheme called data parallelization. So each tile has its ID. So 1, 2, 3, 4, 5, 6, 7, 8. And this, for example, this is 8 tiles, and 8 tiles will be in parallel computing into 8 thread on the computer. And I wanted to talk a little bit about this bad practice of the parallel computing. So it's so what happened to do is usually in the computer, the different threads are not communicate with each other. So when you have a big object and each thread need to know what is this. For example, I will have to read a digital terrain model into my thread, and you don't really chunk that before you go to the thread. You have to read this digital elevation, the whole digital elevation model into the thread in order to do parallelization in the thread. That caused the problem. So you duplicate, you basically will duplicate this kind of image. So for example, when you have the single file, we can chunk it before I go to the parallelization. But you also in the middle of the parallelization, you add another global big one. Global variable, and this kind of variable will be copied into each thread, and that will create a memory increase, memory use for each thread, because each of the thread, they are not communicating with each other. They don't know that I can access this data from another thread. So in this way, you create a lot of time just to do the I/O when you read this global variable into each thread. And the best computing is, for us, we use S3 as the object system. So it's like a cloud optimized format. So when we query the data, even like this is one single big file. If I send a query to this object, we only receive a chunk of the data from the object. In this way, we can communicate with the data as we only use partially the data into my thread. And using that, I can call the global objects, no problem, because I don't really read the object when I go into the thread. And the thread knows, okay, I have this object information. I want to query this mosaic from this object. So I do the query, and I don't read the whole global variable. I only do chunk of the variable into each thread. And this is the better practice that we were saying we will call like good parallel case scenario. So to be remembered that a little bit knowledge of the good and bad parallelization at the basic. Yeah, and that's one way we talk about, like, it's this kind of data parallelization. So each thread we have the data, and we compute and go to each core, and we compute all these kind of, okay, terrain variable, hydrology variables. But you also have this text parallelization. So you can also reading the tile, and I want to compute, for example, slope, hail shade, topographic gradient index. I can copy all this data into three thread and then compute individually, and then output to tell to the local. So this is called text parallelization. And at the end, we would design the pipeline. Okay, we have all this parallelization knowledge, how to build a great strategy to compute all these variables. So in this way, you have to know that what the kind of variables you wanted to compute. In this scenario, we wanted to compute the global digital terrain model for slope, for LS factor, so length slope factor, and the topographic gradient index. And also we can compute some curvature and hail shade. And if you know hydrology, you will know that the LS factor and the topographic gradient index will depending on slope also. So you also need to compute slope first and specific catchment area. And in this way, this kind of, how can we design the best strategy to actually do the data parallelization to from the digital elevation model to slope, and to actually produce 1, 2, 3, 4, 5, 6, 7, 8 layers is the topic for today. So this is some process that we do, and then we check the monitor from the screen. And yeah, maybe I want to show this first. So let's do some hands-on. That is actually what we did when we moved the server. So me and Leandro were connecting the cables. All right, let's first do some hands-on. So yes. Wait, any question to this before going ahead? No, sorry. No or yes. So we used to have like an in-house server in-house, and now we moved to data center. So we used to have our own cooling system and stuff. And now when we think we increased the number of the server we have, we found out like cooling server of a current AC is not working. So we moved to a data center. So we still have our own configuration of all of the server that we are currently using, and we bought them and we install them by hand. And yeah, they are now in the data center somewhere in Ada. So it's not in our office right now, but we still own them in OpenGeoHub. Any other question? Okay. So so if you go here, I will like to show a little bit of the slides. I forgot that I should also mention that we will work on this two library, as we say in the beginning of the section, the name of the section. We will work for this WhiteboxTool and GRASS. So I will kind of introduce when I go to this library. So let's see. So first, can you guys open the GitHub? There's one place you can go from the link to the code lab. Go here. click the link. You'll go to the Colab. Does anyone get into the link, or you can just also you can run it later? It's just the showcase of what we're gonna do. How do we compile in GRASS GIS and to run all these parameters? So the first one is the geomorphometry using GRASS. I think it's the topic. So if you keep running the code, okay, it's not authorized run anyway. The first few line is to install all these packages. So we have to install this Ubuntu GIS and get installed the GRASS Core and GRASS Dev. Oh, I forgot the internet is slow. Yeah. Very good. I'll close my internet. I can use my oh. It's always this bad in this room. Right.
No, yesterday it was fine.
Yeah. Yeah, when people start doing that.
Or disconnected by the meeting.
I also disconnected by the meeting again. I'm sorry. Okay. Can anyone go to the Colab, or you have also the internet issue? Okay. You can try to compile all these packages. This is in Python. I thought in Python environment. So by the way, so I thought it's faster than R. Yeah. Okay, I have installed this, and also I installed this package called raster.io. This is the package to do basic raster geospatial data, raster data accessing stuff. And also introduce a bit of the GRASS. So GRASS is the open source project that developed by the open source developer. So it's a lot of people and around the world. And it's this geographic resource analysis support systems. So it supports a lot of different geospatial processing functionality. And they have the version right now is 8.4.1. And in this way, we just using the DevOps download. So in the Google Colab, you already get the latest version, which is 8.4.1. And we're gonna use that, and also this GRASS session specific for Python library, Python environment to run the GRASS. So when you run this, you can set up the environment for the GRASS until the line 6. Yeah. Can anyone compile, or it's struggling? No. Yeah. Somehow the internet works, somehow it doesn't work. Yeah. Well, if you cannot compile, focus on the lecture, and then you can always access this Google Colab at home, so it's also fine. So in here, we wanted to wrap this GDDM30 into the small area. And then you go see this one. Okay. It's actually a super huge file. So I will show you. I'll just show it to the room. So it's on our server. So we are accessing this file, this one. No, this one. This one, 250 gigabyte file in a single T file. This is the file that we're accessing right here. So if you go here, it's the same file. Just please try not to download it. You will fill up your computer. But using this raster IO, we're able to get like a small bump. This path to our S3 server, and then we select only the window, and then we can read only inside the window. And then later on, we output a disconnect again. Can you please disconnect? Well, they don't like me. Yes. Okay. So in this way, we can kind of crop to the small boundary that we defined here. So this is my small island. So you can see. So we executed. So they were reading this kind of URL path. It's finished so fast. So it will reading the URL path and also crop to the shape that only 6,000 and 8,000, 6,000 in width and 8,000 in height. So this is the data that we can find. I think we can visualize it also. I hope it works. Okay, it's still a little bit struggling in Colab, even on this small image. Okay, this area is not cool, but you can see the shape of the island. Okay, this is not cool. Okay, I'll delete this line of code. And then we can run some GRASS function with this. So in GRASS, you will have to import this GRASS strip and GRASS Jupyter. So you can run the GRASS on the Jupyter notebook environment. And in here, in GRASS, I think the most unique, or I would say I'm not a fan of, is you have to create a my set that give location of where you're rastering, and what is the projection, and what is the so it's like a map set layout to actually read in GRASS in their format in order to run the GRASS. So in the Python environment, you have to define a section and give in the path to your local place. So I just keep it like a temp GRASS data and give it a location, and then create projections. So I reproject into the UTM of my area in order to calculate the curvature. So in the GRASS, you also need, I can just run it and explain on the way. So you only need, you will need to have to read into the GRASS format. So this is R in GDAL. So you read the T file that we save on the local at here, this T file, into a GRASS environment and define in is as DMDLSM. And why we're calling DM? Because our T file is actually in so we define this file. So because we defined this file, it didn't really show. I'm sorry. Okay, it didn't really show. We define this file basically in decimeter. So we have to also use this scale to transform into meters. And using GRASS, they have the map calculation that you can do like simple like metric calculation. And after that, we will do Gaussian filter before we enter any parameterization. In this way, it's just to kind of filter out the extra noise that we could have on our digital terrain model. And then we can derive hail shade and minimum curvature, per fold curvature, and then going to hydrological layers, we have to fill the depression. And then we can able to calculate the topographic wetness index using this function called R watershed. So this is the way of calculating it. And I'm a little bit struggling because in order to calculate in Python environment, you have to open a section. By open a section, you have to read into GRASS every time. So I cannot do like individual tasks. In that sense, I need to create a section again and by again. So I just create one section and run all the code in a time, and then I save how many seconds I run for all of the function. So we can basically see that to run all this function, we spend most of the process are running really fast, like 3 seconds, 2 seconds. But to fail depression, it took pretty long, 38 seconds, and the topographic wetness index take 31 seconds. And this is just for a small boundary that we have. And if you try to do a bigger boundary, like what I do, it will go increase a lot of time. So that's a thing. So this boundary is for like the whole country, and it will take longer than this one. And this already takes 38 seconds. If you have 10 times bigger, it will take 380 seconds. And compare the size from Taiwan to China, you probably calculate the whole China. You take like a whole day, you still haven't finished that. So it's the things that why we need a HPC for doing that. But yeah. And another example is the Whitebox tool. So we also have the example code for the Whitebox tool. If you open the second one from, oh, it's not this. I'm sorry. I am here. If you go here to have the second one, you can find the Whitebox tool version of calculating all these variables. And in this one, it's relatively simple because the developer have already wrapped up this Whitebox tool into a Python version of compilers called Whitebox workflow specific for Python environment. And this packages, according to him, is one of the more efficient way because he used internal array to format the data. So it's not all in flow 32 or not in flow 32 anymore. You can specify from the input data. So if you have an integer 16 and you only read the data format into integer 16, so you don't have to change to data format. And this is relatively fast if you do consider like data compression from the byte number you have. So we do the same thing here, the same function to read the GDTN data. Yeah, and in Whitebox tool, we have to create an environment. So we import a Whitebox workflow, and then we create an environment, and then we read the raster based on the layers that we define. So let's see here. I'm still compiling. Yes, I read this layer. Just gonna see. Okay. Oh yeah, it's there. Okay. So in this place, I can read this. To mention that in WhiteboxTools, also in I think also in GRASS, we can define the number of cores. I didn't write it here, and I'm so sorry. So if you go to so if you do this number of cores, define. Yeah, this one. Pork. If you put it there, you can actually assign how many numbers of cores you wanted to use into computation. And this way, if I use -1, I can assign every core, every thread into the computation, and I can see from here how many cores I have. I think no, from here terminal. Oh, it's super slow. Equal. Okay. Usually I can load the terminal. Anyway, I just wanted to show that in Google Colab you only have 2 cores. Oh yeah, it's coming. I don't think they have this. No. App. Get. Okay, that installed this. Boom. Does anyone have a question to run in this code?
Yes.
Yes?
So, did you consider using Saga GIS?
Yeah. We also tried a bit Saga GIS, and I should also put in this presentation, but I did not because simply we test a little bit out of the Saga GIS and the GRASS GIS and the WhiteboxTools. We found that they have more I would say like they're using more cores but not more efficient in a way. So we didn't include that, but we also have like a lecture that we compare using GRASS GIS, Saga GIS, and WhiteboxTools to map the terrain. This is one of the video. I also have the talk last year in our Open Earth Monitor summer school. So it was also including this there, but in this lecture, considering of the time, we didn't really include that one in here. But also we focus more on the high performance computing, so I switched a little bit of time to there. But you can find in there if you want. It's also on the page. So I installed this. Is that answer your question?
Yes, yes. Thank you very much.
Yeah.
So I conclude that the white box is the most efficient among the three.
I think it's more simple for initial user. But the GRASS has more open source add-on that you can use, but also require more software development skill to actually align different versions. But the WhiteboxTools, they have a very good wrap-up from the initial code, so it's really easy, handy to use. But I would say that this performance for both of them are pretty much the same. Depends on what kind of algorithm you run. So you can see that in here, you only have 2 cores, which is so sad. It's not even like. So I do 1 course is it's so sad that we don't have anything to actually use from the free version of Google Colab. So I can run this, which is very slow. So I'm not really satisfied if I teach high performance computing, not really using high performance computing. So I want to go here. So I will connect in using VPN. So you don't have this environment because this is our own server. So you can just take a look at what we guys are using this performance computing to do. So just to have a taste of the high performance computing. So I have a folder here, and I have a small Jupyter notebook here to actually introduce about this high performance computing. So you can see here, okay, we have a 96 cores, and we have 1 terabyte of RAM for this server. And in the server, we have about 15. So now I'm just using one server to showcase a little bit of this process. So in this small notebook, I also want to introduce about some component of the hardware. So you also get a taste of what to actually create a high performance computing. So if it goes through this notebook, we will know a little bit of the this hardware, and then how can we use it for geometrical computing. So the first one is the including on computer nodes. So you can see that there's a concept of the processor and the threads. So usually in the virtual world, we only consider threads that we're using because this is the unit that they actually relocate the computation. Because for each processor, for example, here, the physical unit is here, they could have a different number of threads in each processor. So each one could have 2 threads or 4 threads. So you can have 16 CPU in one HPC server, and then if you have 4 threads, you have 4 threads in each processor. You will have 64 threads in total. So this is the unit of the processor and the thread. And in our server, we have, I think, 8 threads for each CPU. So it's about 12 cores that we have in one. And you can also check the number of threads that, okay, check number of threads in Python. Let me see. Not here. I think this is a typo. Okay. Probably this one can work. This is very old code. This is probably Python. It's too old. Why is it too old? Okay, it's very stupid. They don't have. Okay, this will work. I found it. Okay, they count the CPU. Okay, they got the code, of course. Anyways, and the second one, the component I wanted to introduce is the ROM. and the ROM is the stand for random access memory. So it looks like this. And this is the temporal storage for data and machine to store the temporary data into fast access environment. So if you see over here, this bar is the memory, which is just random access memory that you can get from each server. So each kind of stick here have some small chips over there, and this is how many they will specify how many kind of gigabyte of the ROM you can have for each chip. So you can easily go to the big server and then replace all this ROM to increase the ROM of your server in total. But somehow also you have to consider some of the brand they are not compatible, so they could fail, and then you have to redo this ROM. So, but this is more or less the way that we also do in OpenGeoHub. If we want to increase the ROM, we will buy some this kind of chips, and then we replace the ROM on in our server to see that we can increase the ROM. So when we do edge top, we can see this. And also for the driver, there's two different driver. One is SSD and one is HDD. I think you guys familiar with this? Could be. So the SSD is the fast to have a fast access, and HDD is like a spinning disk. And most of the time you use HDD to store the data that you don't touch that often, but it should be somewhere in the server. I mean, most of the storage we use HDD because it's more financial option. So so this is how we also consider to have some HDD in the storage server, but use SSD to have a processing server with some specific number of the kind of like storage space in the processing server. And last but not least is the network. In the HPC, we somehow use InfiniBand. Have anyone heard about InfiniBand? So it's like another protocol than the typical Ethernet band. So I'm not even using the Ethernet cable, but if I use Ethernet cable, you know that the internet will be more stable. But this is the upgrade version of the Ethernet cable, and I can really showcase a little bit of this two network protocol and what is the difference. So imagine that we wanted to get the data from my server. So this is one of the data paths, and this protocol we assign here is through the Ethernet cable. So that's why we assign to physical place in our server. So we define this IP for the Ethernet cable, and so we can try to download this. So it's about 20-30 megabyte per second, because you see that it's not the internet speed right now. It's the internet connection speed in our server. So between the storage and the processing server, they have the speed of the 8 megabyte, for example. And then if you switch to another protocol, like here, then okay, it's also pretty slow, but it's I don't know why it's also pretty slow. It's a problem with the internet right now. Yeah. Wait.
Yeah.
It's much faster, but it's still slow. So it's supposed to be 400 or 500, but you only have 40 megabyte right now. Oh, maybe someone is using the server.
It's always happening in the demonstrations.
Yeah, but maybe my colleagues is now computing something, so they occupy the bandwidth. I will ask them in the chat. Yeah, I don't know why when you do the demonstration, it's supposed to be kind of like 40. Okay. Anyways, I don't know. It's supposed to someone using this, and now you see it's going down. It's going down.
Did you stop the first one?
I stopped the first one. Yeah, I stopped the first one. Let me remember this number. Okay, 10. Okay, I'm gonna go back to see how fast it's get.
Still have 20 minutes, by the way.
Yeah, I know. I think it's okay. But this one is also fast. Okay, it got slower. I don't believe myself right now. What I'm doing. Yeah, it's anyways most of the time. So you now get to 30 megabytes. Very interesting to see. Okay. I was testing there before, but it did work, and it did see the difference. But now I didn't see the difference right here. Okay. Okay, let's finish the test. Okay. The second one is doing the same thing, compared with using the Google Colab, and then here using the our own server infrastructure. I hope they don't occupy my server right now, so I don't slow down my process. Okay. Okay, I didn't extend my license. I get banned from the Premiere version. Do I have a license? So I can call the function from here.
The WhiteboxTools only works on smaller rasters, the free version.
No, I think there is some extension function that I got the premium.
Oh, so you can actually have a subscription for it.
Yeah, I think so. Why bugs?
And what did you actually end up using? Whitebox or GRASS for the maps you derive?
At the end, we use Whitebox for some, because it's we encounter some memory leaking issue using GRASS. So when we do parallelization, and it ended out to have and so memory issues is kind of like pretty bad when I do long-term processing. So somehow they will stop at random point. I don't know what happened. So you can run like small scale and scale it up, and theoretically it will work, but it ends up to be like memory conflict, and then the process crash. And in ROS, it's more like you have to be memory safe in order to run that. So usually if you don't constrain the good at your memory, for example, you do double parallelization, it will already like kill you at the beginning of the parallelization. So they're written in a language called Rust in the WhiteboxTool, which have a very strict specification on memory allocation. So in that case, for the HPC, we think that it will be a good solution to use. So we end up using the WhiteboxTool for that. Yeah. Well, so I want to show a little bit. So people ask about the Whitebox workflow. So when we go here, I think they have a pro version that you can actually extend a bit of the functionality, but I would say using the free version, some like topographic rendering that's slow or hell shade already, it's including in that version. If you do basic geomorphometric variables, it's okay for there. So you can visit this website here and to get, but I'm not using this. Okay. So let me do the same thing here to retrieve the raster, and then we can start some process. So we can define also this one. Same thing we're doing from here. Read the raster. So okay. Let me see if it's speed up for the Gaussian filter. I cannot see. Feel like, can I disconnect for a bit? Can I disconnect?
From the code?
Yes.
Okay.
Yeah. And also from the sharing.
Yes.
Okay. So if I don't share, they will also disconnect from the code?
You will not disconnect from the call, but the call will not record what you're showing.
Okay, cool. Because I'm gonna check the password. Huh? Okay, we can come back. I have 10 minutes left. Mm. Okay. So I want to show a little bit here from the terminal. So I have all these threads. When I run the function from the Whitebox tool, okay, using this server, for example, this calculate Gaussian filter. Wait, it's too fast. It didn't really catch up. Okay. Okay, the area is too small, but you can see the bar moving slowly a bit, but you already finished the computing because maybe the area is too small. It's too fast, but you can see the Gaussian filter here take about 0.69 seconds, where that you calculated from the Google Colab, it's 7 seconds. So that's the same code that we run in the HPC compared with so you can run another function, also take a look of the time. Also, you run pretty fast to finish because they parallelize into different cores. And this one also. Yeah. And this one. Yes. And this one also to show. So I hope this one go what I expected, because nothing go really for what I expected. And so it's pretty. So now you can see this function is actually run pretty long. So it's so basically this function field depression, as we described, you have to go and search to find a lower pixel in order to see that how can so the field depression algorithm is based on to connect the hydrology to connect the flow on the hydrology analysis. So when the pixel flow from high point to the lower point, it will probably because of the noise of the digital elevation model, they can stop or string at the random point and become like a lake. And in this way, it's not a real lake, but it's because of you don't really make the hydrological connection. So in this function, you try to search all the scheme of the digital elevation model and find out there's like some small pit, and fill up this pit to a certain level so water can flow through the pixel. So in this function, they actually have to do pixel by pixel. So there's no way the function has been implemented in parallel, because when you think about doing this in parallel, you're doing A pixel, but B pixel also get altered, and they cannot really like do. It cannot really make it connected. So in this function, the implementation, they make it. They just cannot implement it in the parallel way. So it takes longer to compute, even like you have a lot of cores. So this is one of the things that, you know, when we develop it, we also found out this issue. So you kind of like spend most of the time, which is the bottleneck, running this function, but the servers cannot run other stuff because it can be occupied by this function that running in the background. And so this is kind of like an issue when we do high performance computing. So this is why we always come and check off the terminal to see that if the pixel really do parallel computing or not. For example, this one, yes, really small, so, but it really go a little bit up only. Yeah, I probably need a bigger bounding box to show this. So anyway, I think I'm pretty much running out of the time, but let's cover most of the topic I wanted to say. So yeah, this one is really showed okay because this one is bigger space. So if I get a bigger pixel, you can really show that the bar got computed, because in before it just like a blink, so you didn't really see, but now you can see that they actually run the computer because I increased the bounding box size. So that is how actually using for this performance computing, high performance computing for doing this kind of job. All right. I am okay. A question before I go back to
on the map layers that you produce from this, like, where the totally available open.
yeah.
Yeah. I understand the precision of those, like that data is kind of like on the several meters scale, is that right? Like the precision of the elevation. So in countries such as the Netherlands, you see that kind of in the layers you derive, such as SOAP or GWI, it's actually challenging to use that data almost at like the field scale or farm scale.
Yep, sure. I think it's if you have better data, why you use the worst data, and doing this. So Netherlands have the AHN project. I don't know how to actually pronounce because I'm not Dutch. So it's like a 50 centimeter right now, 50 centimeter elevation, digital elevation model, to use that for most of the stuff in the Netherlands. But this global project is not only for Europe, but also for other places that they don't really have data sources for the elevation. And using that can at least provide the country have all these data sources. But also, what we think about doing this project at the beginning was also because the nature have no boundary. So you can have the country, but the watershed is actually across different country. And if you think about that, you only have the data from your own country. You cannot really go beyond to actually analyze the watershed that's across the border. And there's some certain issue that happen in different countries, the fighting for the water source and stuff, and create this kind of open source data set for kind of include the global data in the ways that to be consistent on the global data set, but also provide the data sources to some place that they are not accessible to this kind of data. Yes.
Yeah, and it's pretty impressive.
Okay. I don't think my presentation was impressive. Yeah, because I just have so many technical issues. And yeah, so we'll talk about a lot about what we are doing, but essentially what we also think about, like, to bridge out the difficulty from learning everything to actually produce a data set. And is that really necessity to be like implemented for anyone? We don't think that is just a way. So we create this paper, but also projects called GDM30 to actually create open data places the M30. To help generating this digital elevation data set for the whole world. So this is based on the digital elevation model, but also the derived parameters of all this digital elevation model of the landform, line curvature and stuff. And then we also received some kind of like collaboration or request to actually include more different kind of like terrain variables. And this is the ongoing project that OpenGeoHub was hosting. And then we do use our high performance computing that I taught today to derive all this layer in the reasonable scale time. And then we provide this data as the analyzed ready data for open community to use. So that's why we also set the license to CC by 4.0. So you can either you can even use it for commercial without having the licensing issue. So that is the ongoing project we're having right here. So this is the GitHub. And the last thing that was working with this project, and I have the email with the developer of the WhiteboxTools, because we use that, and then we found out they have very weird performance when we do the fault depression on the coastline, because the coastline have the longest processing time. It's also interesting because I talked with him, the guy, so I kind of like anonymous this guy. So I talked with him that I have a problem with the coastline or digital elevation model, what's happened, and I tried different method, and I create some code and I sent it to him, and he run it and also encountered the same issue, and he found out it's actually his wrapper for the GeoTIFF, that he actually do not mask out the GeoT, so you always try to find lower pixel on the empty ocean places. So they find like very long time, like 6 hours, just to try to find a lower pixel for every different pixel. So I just write an email to him, and he found out this issue, and he kind of update this new version of the Whitebox workflow, and he end up to solve this problem 10 times, 100 times faster as I run as a coastline area. So this is the last thing I want to show. Just shout out to like open source community. There are always people like working there, trying to help a researcher to develop the product, to run the software, do the research, and then we should also support and appreciate those people that are working on the back. So that is my presentation, and then like thanks